Welcome to Calculus 1, Lesson 1B.3, Continuity. Function is continuous if it can be drawn with one stroke of the pen. We went over this a little bit in the last session, and I gave some examples, some drawings of what it looks like to be continuous versus discontinuous. We also talked about how you might not be continuous everywhere. You might be continuous over a chunk of the real line, or you might just have particular little spots where it's not continuous. Today we're going to expand on this a little bit more. A function is continuous at some point c, f of c, if, and only if, the limit as x approaches c at that value c is equal to the function evaluated at c. Okay, so there's a lot to unpack here. First, what does if and only if mean? If and only if is an implication that goes both ways. It means one implies the other and the other implies the one. So an example of what may not be an if and only if is if it is raining, then I will bring my umbrella. I might bring my umbrella if I think it's going to rain, even if it doesn't end up raining, right? So that would be just a plain if. But an animal is a dog if and only if it's got, no, that's not a good example. An if and only if means basically these two things are equal. They are true in all of the same circumstances. So in other words, the statement a function is continuous is equivalent to the statement the limit as x approaches c of f of x is actually equal to its function value at c. Okay, now what does this bit mean? I know we're still kind of wrapping our heads around what a limit means and how the x is sliding around to get to the c and the effect on the y and all of that. It means that your c, when your x slides closer to that c, it wants to settle on the function value and stay there. In other words, your y value wants to rest in a certain place, and that agrees with what the function actually evaluates to. So how can we be discontinuous? These are the only ways when you break it down. If you're not defined at C, then you can't be continuous there. Because if you're not defined there, then f of c doesn't exist. Okay, if this doesn't exist, we can't state that it's equal to any particular thing. If the limit doesn't exist, technically you could have the function value exist, be defined, but still have the limit not exist. Or any other situation where the function value and the limit do not agree. Visually, the main ways to be continuous that we see in the problems that you typically work with in a Calc1 are your jump, your removable discontinuity, also known as a hole, or your asymptote. There could be other ways, but these are the main ones that you're going to see. So here's how to check to see if a function is continuous. For a function f to be continuous at c, all three of these must be true. So we're going to zoom in on a particular point, c, and ask, are we continuous at this point? Well, imagine saying the opposite of these things, the opposite of how to be discontinuous. You need f of c to be defined. You need the limit as x approaches c of f of x to exist, and it needs to agree with the function value. I guess we're getting a bonus lesson in logic today. If you think about it, this is an or. A function is discontinuous if 1 or 2 or 3 is true. negate that, invert that, make it say the opposite, right? The opposite of discontinuous is continuous. The opposite of an or becomes an and. So for a function to be continuous, we need 1 and 2 and 3 to all be true at the same time. Okay, so to show that it's continuous, we need all three of these things. In order to break continuity, we only need to have one of these things. Okay, so if any one of these things is not true, then you're discontinuous. So that's at a point. We can also talk about continuity on an interval. Suppose A and B are real numbers. Remember, we have that element business. Element means it just lives in that set. So A and B are any real numbers, and A is the smaller one. A function f is continuous on we're talking about the open interval AB. Let me stress this here because AB almost looks like it wants to be a point, right? This is an interval, not a point. If the function is continuous for all possible C in that interval. That's not too surprising of a definition if you think about it. Here we also allow for A and B to be plus or minus infinity. So you could say any number greater than 6, we're going to be continuous there or not continuous there. Remember in lesson 1B.2, I listed all kinds of common types of parent functions and discussed where we expect them to be continuous or not continuous. Let's try an example. Discuss the continuity of y equals 1 over x. First of all, is it continuous at x equals 17? Okay, so let's run through our 3 checks. Is f of 17 defined? Yeah, that's fine. It's defined. Check. 2, the limit as x approaches 17 of f of x. Limit as x approaches 17 of f of x. Well, in this function f of x, which is equal to 1 over x, is there anything stopping from x going to 17 there? No. That limit will exist. But is that limit equal to its function value? Yes. All right, we said that rational functions, we can use direct substitution so long as we don't have any divide by 0 issues. 1 over 17 is not 1 over 0. Check. So yes, it is continuous at 17. But 17 isn't all that interesting of a number. It's prime, so I guess it's a little bit interesting. But there's plenty of other numbers out there. Let's talk about an arbitrary non-zero real number. Is it going to be continuous at such a place? Okay, well, if C is some arbitrary, C is any number but 0. If C is any number but 0, does f of C exist? Yeah. Because 1 over C will not be 1 over 0, and that's fine. 2, does the limit exist? Limit as x goes to C of 1 over x. Okay, well, since C is not 0, there's no funny business here. Since C is not 0, trying to divide by C doesn't result in any divide by 0 errors. So we're fine. And does that limit agree with the function value? Is this equal to 1 over c? Yes, by the same logic that we said with the 17. Okay, so this proves that if c is not 0, then this function is continuous at c. I'll put that down here. If c is not 0, then this function is continuous at c. Okay, what about if it is 0? If it is 0, f of 0 tries to be 1 over 0, which is not defined. Now, technically, I only need to break one of these three things in order to say that it's discontinuous, right? I can technically stop right here. But let me show how the other two things get a little bit messed up as well. Does limit as x approaches 0 of 1 over x exist? No, it doesn't, because as x approaches 0, the y value decreases without bound over here, increases without bound over there. And if that limit doesn't exist, and if the function's not defined there, then those two things can't be equal. So it's a triple threat there of not working out for continuity. So it is not continuous at 0. So you can say it is continuous on, you could say, the set negative infinity to 0, union 0 to infinity. Or you could say the set of all real numbers x where x is not 0. Whatever notation you prefer. Right? These can be pretty easy to picture. So why don't you pause the video here and see if you can figure out this next one on your own. Discuss the continuity of f of x equals x squared minus 1 over x minus 1. Notice that the top is going to factor x plus 1, x minus 1. Okay, so f of x is almost everywhere equal to x plus 1. It's not quite equal to x plus 1 because those two things are going to disagree when x is equal to 1, right? They're not literally the same function, but these two functions are equal everywhere except for 1. Okay, so there's the big question. Are we continuous when x equals 1? No, because f of 1 is not defined. Okay, so because we just broke one of the three checks, and I had an index card, here we go. Because we broke just one of the three checks that we need, we can say it is discontinuous. Therefore, discontinuous at 1. If c is not equal to 1, is it continuous? If c is not equal to 1, then c squared minus 1 over c minus 1 is defined. Because if c is not equal to 1, then c minus 1 can't be 0. Okay, c minus 1 is 0 if and only if c is 1. There we go. There's another example of an if and only if. C minus 1 equals 0 if and only if c equals 1, right? Like those two things are true in all of the exact same circumstances. Okay, so it's defined, the limit as x approaches c of f of x here. Since c is not 1, we don't have any divide by 0 funny business, and because this function is rational, that means direct substitute works and we'll agree with the function value. Okay, so exists and is equal to f of c because rationals only fail to direct substitute at places where the denominator equals 0. So overall, it is continuous everywhere except for 1. So it's continuous on negative infinity to 1, union 1 to infinity, or the set of all real numbers x where x is not equal to 1. All right, next example. Another good stop to pause and try on your own if you so desire. Discuss the continuity of a piecewise function where the function is going to return x plus 1 if x is less than or equal to 0, and x squared plus 1 if x is greater than 0. All right, so if you're going to pause the video, go for it. Otherwise, let's continue. If x is greater than 0, is it continuous at x? Well, if x is greater than 0, then g of x lands in x squared plus 1. So we're on that purple branch of the function up there. We're somewhere over here. That's a polynomial, and polynomials can be direct substituted. Okay, so the limit there will exist and will be equal to the function value. Well, x is arbitrary, so I'll just say function value. So it is going to be continuous at any positive number. What about if x is less than 0? So if it's negative. If x is negative, then g of x is going to be equal to x plus 1. Okay, by the same logic, that's a polynomial, so the limit exists and is equal to its function value. So yes. What about right at 0, where we switch colors, where we switch from one track of the piecewise function to the other? Okay, well, is f of 0 defined? Yeah. If x is 0, then we fall in here and we do 0 plus 1, which is 1. Okay, what about the limit? limit as x approaches 0 of f of x. Now, what did I say about what it takes for a limit to exist? We have to settle on the same value no matter which direction we approach from. The two directions have to agree. So for a limit to exist, we need this to happen, like that. This means does not exist. That means does not exist. Even this would be does not exist. Okay, for it to exist, this has to happen. They do meet up right there, right? Could I take the little or equal to symbol out from under the blue and put it in the purple and still have the function be the same? Yeah, I could. Because both of these tracks evaluate to 1 at 0. Okay, whether I plug in 1 into the top one or the bottom one, I'm going to get 1. Okay, so f of c is defined, f of 0 is defined, it's equal to 1. The limit as x goes to 1 exists, and it is equal to 1 as desired. Is there anywhere that this function is not continuous? Well, all numbers are either positive, negative, or 0, so this function is everywhere continuous. Or instead of saying everywhere continuous, you could say it's continuous for all real numbers. You could say blackboard bold R, or you could say interval negative infinity to positive infinity. Now, it might feel like kind of a stroke of luck that those two branches of the function landed in the same spot. What if I just took away that +1 there? If I took away that +1, then I'd be looking at this line instead. If I could draw it properly, there we go. It would look like that. Okay, if that 1 wasn't there anymore, but this one stays, right? That would be this line. And then we would be having this situation, because from this direction, we'd be hitting 0. And from that direction, we'd be hitting 1. So visually, we already have this idea of the two different sides of the limit and whether or not they agree. So next, we're going to put some notation to that. We're going to talk about something called one-sided limits. If I take a limit, but put that little minus sign up there, that means we're going to approach C specifically from the left side. Now this isn't, you don't just put a C and then a minus sign, kind of like that. It's almost like the minus sign is being an exponent instead of trailing off to the side of it. Not that I'm gonna like take out a magnifying glass when I'm grading your papers and see if it looks like an exponent or if it's on the side, right? Like it's not that big of a deal. I just wanted you to know how it should be done properly, maybe if you were to typeset your math or something. So x approaching C minus means approach from the left or left-hand limit. If I put a plus sign up there instead, so again, the plus sign is going to end up looking like a little exponent and not just off to the side. That means we're approaching C from the right, or taking a right-hand limit. When you don't see either of those symbols, so if there's no plus or minus at all, then it means you're approaching from both sides, called a two-sided limit. All right? Now, the two-side limit is only going to exist if the left and the right agree. Look at an example here. Here's another good place to pause your video and see if you can figure these out before I go over it. All right, let's go over it. Find limit as x approaches 0 from the left of this function. So this is behaving very similar to the one over here. I mentioned maybe moving that down to x instead of x plus 1. Instead, what I've done here is actually we left the line alone and we moved the line up 1 and we moved the parabola down 1. So now they're not meeting in the middle, huh? If I approach 0 from the left, I'm following along that pink line right there. So as x is sliding into 0 from the left side, the y is going to be sliding up towards, what is that? That's 2. Okay, as I slide along this function here, what is the y value that I'm trying to land on? If I go in this direction, it's 2. What about the other way? This point is filled in, this point is not, but we're looking at the limiting behavior. Where is it trying to go as it gets closer, even if that's not where the function value actually ends up? So from the right, we're sliding along the blue line, the blue curve, down that way. Okay. Now, if I had a ball and I slid it along this parabola here, it is going to roll over that point and then just fall off, right? There's no reason why it would suddenly bounce up here and then continue that way. But it does try to go to the origin, right? As I slide in this way along the blue curve, it feels like the function value wants to go to 0. Okay, so what if I take away the plus and minus sign? So without any plus or minus sign, we're talking about the two-side limit. The two-side limit only exists if the one-side limits agree. Our one-side limits are different here. Okay, this is, if I'm doing my fingers, it's that. Your two-side limits are doing that. So this does not exist. What about the function value at 0? The function value at 0, I'm just going to look at the piecewise notation here. If x is equal to 0, then we land on this track here. This says take your x and add 2. So when x is equal to 0, which satisfies this, we take x and we add 2. Okay, so in some kind of way, the left-hand limit is agreeing with the function value, but the right-hand limit is not. Therefore, the two-side limit does not exist. Okay, so now that we know something about two-sided limits, let me talk about a situation where you have a function that isn't necessarily defined on the entire real line. So we're going to have a restricted domain here. Right, this function is the top half of a circle. And actually, if you were to take function, what would that be? X squared plus y squared equals 2 squared. If you were to solve that for y, you would get plus or minus our function here. This can't be solved explicitly for y because of the squared, and that means you're going to have a plus or minus when you try to get y alone. Okay, so what is the domain of this function as presented here? Just the top half of a circle of radius 2. Visually, we can see that the domain goes from -2 up to +2, and it is defined at plus and minus 2, so that will be included in our domain. Algebraically, you could say, well, radicals get angry when you try to put negative numbers under them. So you would say, what makes 4 minus x squared negative? 0 is okay. It's allowed to take a radical of 0. That's okay, just not a negative number. What you would find is we would have to throw out anything that is outside of -2 to 2. So the domain is -2 to 2. All right. So now let's discuss continuity in a couple different spots. How about at 0? The function value at 0 is going to be 2. And near 0, if we picture approaching from the left and from the right, it goes like this, and they meet up right there. So here is the left-hand limit going to 2, and here is the right-hand limit going to 2. And they agree. So f of 0 is equal to limit as x goes to 2 at 0, not 2, of f of x, and both of those things defined and exist and are happy. How about at 1? This should say yes, not f of 0 equals 2. How about at 1? Same situation, but now our point's over here. Okay, so f of 1 is going to be the y value right there. You could do some trig and get a decimal approximation for that if you so desired, but let's not and say we did. Whatever that is, I know that it's a real number. And I know that as I slide an x value in from this direction and from this direction, they're going to the same spot. Okay, as I approach 1 from either side, they agree and settle on the actual function value. So by the same reasoning, this is continuous. Okay, and those are just two little spots, two little examples. If C is any number that is in the domain besides the endpoint, so C is anything in here excluding the endpoints, is it going to be continuous at that point? Yeah, it is. And everything in here can be drawn with one stroke of the pen, so we can see that visually as well. Any point that I want to pick along this half circle, they're going to meet up and agree. And the left hand and the right hand will be the same, and they'll exist, and they'll go to the function value. What about at -2 itself? Let's check all the limits. Limit as x approaches -2 from the right of f of x. Well, as we approach from the right, the function value wants to go to 0. As I slide in here from the right, the y value is getting to 0 and it's staying there. Okay, that's fine. What about from the left? There's nothing over here. I can't slide along anything to get towards -2. There's no way to be there. Okay, I can't talk about, sorry, this is a -2 here. I can't talk about approaching -2 from the left because numbers that are to the left of -2 aren't in the domain. So this limit actually does not exist. In order to be continuous, we need all three of these to be true. We need the function to be defined there. We got that. That's fine. And we need the two-side limit to exist. One of the one-side limits doesn't exist, so the two-side limit can't exist. By the same logic, at +2, the left hand will exist, but the right doesn't. Left-hand limit exists. Right hand does not exist. So overall, where is this function continuous and where is it not? It's continuous everywhere except for those little endpoints. Everywhere in its domain except for those little endpoints. It is continuous on the open interval, -2 to 2. So everywhere except for plus and minus 2 proper. Interesting situation, isn't it? Turns out there's things we can do to figure this out without even looking at a graph. Sometimes we can use what we know about a function and what upsets it in order to figure out where it would be discontinuous. Without looking at a graph, discuss the continuity of tangent squared or tangent of x minus 1. I'm going to put a unit circle over here in case we need that. Okay, and a fact that you need to know is compositions of continuous functions are going to be continuous. So if you take two continuous functions and compose that, that's always going to be continuous. Okay, so where tangent and x squared minus 1 are both continuous, the composition will be continuous. X squared minus 1 is continuous everywhere. Tangent is not. Tangent has many asymptotes. It has asymptotes at the end of each one of its periods. I can show you a graph of tangent function from my purple packet there. Here for you. All right, it's got an asymptote at pi over 2 and 3 pi over 2 and negative pi over 2. It's got lots of asymptotes. So tangent of theta is undefined when theta equals, well, we said pi over 2, 3 pi over 2. We said negative pi over 2. And infinitely many more, countably infinitely many more. So tangent of theta is undefined when theta equals any integer times pi over 2, yeah? Is it multiples of pi over 2 or plus and pi? Oh, that'll do the same thing. Yeah, like negative 1 pi over 2. Oh, no, 2 pi over 2 wouldn't do it. Okay, no, I don't want n pi over 2 here. I want pi over 2 and then add, to get from here to here, we add a pi. To get from here to here, we subtract pi. Yeah, that's n pi. So do we say it's discontinuous when x equals some pi over 2 plus n pi? No, because that is the argument that has to go into tangent in order to make it discontinuous. So we have concerns when this inside function could return a number such as this. Okay, so when the inside function, x squared minus 1, equals pi over 2 plus n pi, for some integer n, it will be discontinuous. Okay. We're almost there. So what x's will make that happen? What x values would make x squared minus 1 evaluate to a number of the form pi over 2 plus n pi? To find that out, we want to take this equation and solve it for x. And n is going to be an arbitrary number. I'm going to keep that as a letter and just let it tag along. All right, so I'm going to add 1 to both sides here. Pi over 2 plus n pi plus 1, right? Now this is, whatever n is, this is just a big ugly number, right? Whatever n is, this is a real number. So to get x alone here, I'm going to want to take the square root of both sides. And remember, anytime you take square root of both sides of an equation, you have to put a plus minus, because a squared will eat a negative. And so we don't know if there was a negative there to be eaten in the first place. So x equals plus or minus pi over 2 plus n pi plus 1. Okay. So for any integer, n, we know that plus or minus pi over 2 plus n pi plus 1, all under a square root, will make tangent of x squared minus 1 blow up. Do you want to check that? Do you want to see why? Let me grab another sheet of paper here. Oh, actually, I've got room. I can do that here. Okay, if n is any integer, and x equals pi over 2 plus n pi plus 1, this logic is going to apply to the negative version also. Then let's evaluate tangent of x squared minus 1 at that point. You have tangent of this x here is going to get replaced with what I declared it's equal to. So tangent of x squared minus 1 is tangent of a quantity squared minus 1, where the x is getting replaced with that big ugly square root. Right? I'll write that bigger on the next line, don't worry. Well, the square of a square root is just the thing itself. So the square and the square root will undo each other there. And then I still have that minus 1 hanging out. That'll cancel with that, leaving us with tangent of pi over 2 plus n pi. And no matter what n is, that's going to put tangent in a spot that it blows up, that it has a vertical asymptote. Okay. So which is undefined. Another way to look at it is if you take the sine of, the cosine of pi over 2 plus n pi. Cosine of pi over 2 is 0. Okay, if you take pi over 2 and add another pi, you get to 0. Add another pi, you get to 0. Add another pi, you get to 0. So cosine of pi over 2 plus n pi equals 0 for all integers n. Tangent is sine over cosine, right? So where cosine is 0, tangent blows up. Tangent is undefined. We don't like that. All right, so overall, where is tangent continuous? Where is our original function, tangent of x squared minus 1? Where is it continuous? It is continuous everywhere but, and I'll put this in set builder notation and just explain how to say it in words. It's continuous everywhere except for the x values where, actually I'll put, there is a way to do that starting with x and r, but this is simpler. It's continuous everywhere but the set of numbers of the form plus or minus pi over 2 plus n pi plus 1 where n is an integer. So it's continuous everywhere except where x is equal to one of those guys. Cool? Last example for the day. Discuss the continuity of, we have a piecewise function here. We have an x sine of 1 over x when x is non-zero, and a 0 when x equals 0. Now, if you're clever, you might go, piecewise functions, those are often going to be discontinuous when the two tracks don't agree at the value in question, right? Can I plug 0 into the top track here? No, because I can't take the sine of 1 over 0. That would be undefined. The top track is not defined at 0. The question we're really asking here is, since x sine of 1 over x is not defined at 0, is this discontinuity removable? Okay, in other words, if we were to look at the graph, we're gonna do this algebraically, but if we were gonna look at the graph, we would want to see that we have this situation, just a little hole that can be plugged by putting in 0. Okay, we want to see a removable discontinuity of this function here where it looks like it wants to go to 0, because then when this track of the piecewise function fills it in, then it's continuous. Okay, if this or anything else crazy happens near 0, then it's not going to be continuous there. Paper sliding. There we go. All right, So let me think. Whatever x is, sine of 1 over x has to be between +1 and -1. All right. So now let me go through and multiply everything by x. Okay, so we have an inequality here. Now let's take the limit as x goes to 0 of all of those things. And you know what? Let me break off on a little tangent here and say something about what I just did, slapping everything with an operator. Um, Let me go back to some operators that are more familiar. If I had some kind of inequality like this, I could say 1 plus 6 is less than or equal to 2 plus 6, and that's less than or equal to 3 plus 6. If that were an equal sign, then I could take any function or apply any operator, and it would preserve that inequality, right? Like if I negate everything, it would flip the inequality around. If I square these, because they're all positive, okay, squaring is an operator. So just as you could square both sides of an equation, you could square each side of an inequality. And as long as everything there is positive, that inequality will be obeyed. If everything was negative, then you'd have to go the other direction. If some are positive and some are negative, then it could go either way. Okay, limits are something that will obey inequalities. Okay, so if this, and this is saying for all x, right? For all x, negative x and x are on the are upper and lower bounds for our function there at that particular x value. Okay, and if it's true for this particular arbitrary x, then it's true for the x's and a little bit of wiggle room around that x. And when you're taking a limit, you're working in that little bit of wiggle room that is near the value you want, right? So that's why I'm allowed to take the limit of all three pieces of that inequality here. Okay, but this gives me something cool because the limit as x goes to 0 of negative x is 0. And the limit as x goes to 0 of positive x is also just 0. And what do we have here? We have squeeze theorem. So therefore, this is equal to 0 by squeeze theorem. I'll show you the card for squeeze theorem so that you have it. Oh, I didn't fill it in. Sorry, guys. So do we have all three of our checks? Is f of 0 defined? H of 0. Is it defined? Yeah, because when x is 0, we fall in this track and we go to 0. So we're good. Does the limit exist? Yes. Does the limit equal the function value? Yeah. Yeah, we wanted it to go to 0, and squeeze theorem shows that it does. Limit is also equal to 0. So yeah, this is continuous. Before we go, I think it'd be cool to show the graphs of those two functions there. Let me switch over to screen share real quick. There we go. All right, here's our tangent of x squared minus 1. And so this is discontinuous for any, it's plus or minus square root of, oh, my paper's way over here. Plus or minus square root of pi over 2 plus n pi plus 1. Let me show you what that looks like. I'm going to let n be some integer, and then I'm going to choose a value. Let's call this big X, and let's say x1 equals the positive square root of pi over 2 plus n times pi plus 1. And then let me graph the line x equals x1. Let me also graph the line x equals negative x1, because there was the plus and minus there, right? So for any integer n that you choose, you get a pair of asymptotes for that function. So if I let n be 1, then we're at these two. If n is 0, then we're at those two. 2 is out there. 3 is out there. 4 is out there. It looks like they're getting closer and closer and closer. That's pretty cool, right? They're not evenly spaced because the n is under a square root. If the n were outside of square root, then your asymptotes would be evenly spaced. But because it's under a square root, the distance between those asymptotes is shrinking down to nothing until your graph looks pretty neat. It's kind of the stuff of nightmares, huh? I thought that function looks pretty cool. Let's look at the other one. Here is x times sine of 1 over x. And, out here for some big numbers, sine of 1 over a big number, 1 over a big number is a small number, so that's acting like it wants to be close to sine of 0, and sine of 0 is 0. Wait, sine of 1 over big number, small, sine of 0. And 0 is 1, it's 0. But then it's times that big number as well. Sorry, I confused myself for a moment there. As this function gets close to 0, it starts going a little crazy. It almost looks like we're walking down a hallway where the two walls are both decorated with sine curves. And I said that whatever x is, the x times sine of 1 over x value has to live in between negative x and positive x. Right? See how it's always in between those two numbers. And so, as we zoom in closer and closer, we can see that our function, this blue squiggly stuff, is squeezed in between negative x and positive x, which both go to 0. Very nice application of the squeeze theorem there. One last question for you. Are you enjoying the jokes at the end of the videos? Because I think they're as smooth as a continuous function. So please don't limit my creativity by asking me to stop. See what I did there? At any rate, there we have it. Now we know something about continuity. Keep practicing and have a wonderful day.